With the invention of the Bessemer process in the second half of the 19th century, the production of steel increased rapidly, which revolutionized the way we design and build structures. With its high strength and durability, steel became the building block of modern cities. Steel made tall buildings, such as the Empire State and the Chrysler Building, become possible. If we pay closer attention to the steel frame of these buildings, we can notice a particular shape appearing in the steel beams and columns. Have you ever wondered why we shape steel as an eye? Well, today we're going to find out the secret behind the eye shape. To determine why the eye is the most common steel shape, let's analyze different types of beams under load and see their behavior. We will compare a hollow square, an eye shape, and a solid circle with dimensions as shown. All beams are made out of the same material and with the same cross-sectional area. I prepared a simulation where a simply supported beam is loaded with a single load at midpoint. On the bottom left, we can see a graph of the applied force and midpoint deflection, and on the right we can observe the yielding of the section. As the load increases, the deflection of the beam increases in a linear fashion. At around 37 kilonewtons, the first yielding of the material occurs. Once the yield point is reached, the beam will continue to take load, however, the deflection will no longer follow a linear line. The beam will start to bend a lot more while not taking much more load. This is because the material is undergoing plastic deformations, which are permanent and characterized with large strains. At around 49 kilonewtons, the beam has gone fully plastic and has reached its ultimate capacity. From this point on, the deflection will keep increasing while the load capacity will remain the same. Now, let's plot the same graph for the three different shapes and see how they compare. Again, on the y-axis we have the applied load, and on the x-axis is the midpoint deflection. The circular shape reaches its ultimate capacity at around 26 kilonewtons. Then the green line, or the square shape as we saw earlier, reached its ultimate capacity at around 49 kilonewtons. And lastly, we have the eye shape, which more than doubled the square shape and reached 97 kilonewtons. As we expected, the eye shape performed much better than the square or circular shape, even though all of them use the exact same amount of material. Okay, so let's load up a beam and look at what's happening on the inside and how the load is being carried. To load our beam, we will use a fake animated hydraulic press. The internal bending moment, or torque, at midspan of the beam for a single load can be calculated as P times L over 4. If we look at the loaded cross-section at midspan, we can notice that the top half of the beam is under compression and the bottom half is under tension, while at the midpoint, or also known as the neutral axis, the stress equals 0. Because these forces act in an opposite direction, as you can see on the diagram, they induce an internal torque or bending moment. If this is not intuitive to you, let's look at a so-called foam beam. At first, the lines drawn on the beam are vertical. However, when the beam is bent, we can see that the lines on the top got much closer together, which means the material is being compressed, and on the bottom, they got further apart, which means the material is being stretched. With that in mind, let's measure the stress along the cross-section of the beam. We can notice that as the load is applied, the stress is higher the farther away we move from the center of the beam. When the stress reaches 300 MPa, or the yield stress of steel, then we mark that as the yield point. If we continue to load the beam, then the yielding will propagate towards the neutral axis. When the yielding reaches the neutral axis, then the beam has gone fully plastic, or it's reached its ultimate capacity. Upon further load, the beam will excessively deflect or rupture. This is the capacity that we use in design of steel members. But in reality, steel has additional reserve strength that we don't really rely on, where the stress profile looks something like the dashed red line. If we multiply the compressive area times the compression stress, we will end up with an equivalent compression force acting at the centroid of the area. If we do that for both the tension and compression side, we will end up with two forces acting in opposite direction of one another. These two forces are equal in magnitude, and when multiplied by the distance between them, they represent the moment resistance of the beam. If we look at the circular section, we can see that again we have the same two forces. The magnitude is the same as in the eye shape, however the difference is in the location at which they are acting. The centroid of the compression and tension side are much closer towards the middle, which significantly shortens the moment arm. And since the moment resistance of the beam depends on the distance between these forces, we end up with a much smaller moment capacity. If we could shift the centroid of the area further away from the middle, then we would increase the bending resistance of the beam, and I hope this video helped you understand the secret behind the I shape. Thank you for watching, and don't forget to subscribe. See you next time.